motion and vectors. So like a lot of things in the real world that involve physical movement, we can use vectors to describe them, and that goes for displacement, velocity, and acceleration. But in order to do this, when we have a look at a vector in our Cartesian plane, let's go ahead and draw one. It's kind of difficult dealing with vectors that are on some kind of angle like this. It's much easier to deal with the x and y components. So another way to think about a vector is that if we let the magnitude of the vector be r and acting at an angle theta, we can go ahead and write some things that might be a little bit easier for us to deal with. So let's just go ahead and draw a little right-hand triangle here. And we know that the hypotenuse here is r and we have an angle theta. Let's call the x component x and the y component y. And let's go ahead and write some expressions for sine theta and cos theta. So sine theta is just going to be your opposite over your hypotenuse, and cos theta is going to be the adjacent over the hypotenuse. So y is going to be r sine theta, and x is going to be r cos theta by multiplying both sides by r. And what that means is, if we have this situation over here, this distance is r cos theta, and this distance is r sine theta. And we could express this vector u as r cos theta I plus r sine theta j. And this is going to help us in solving some questions involving motion and vectors. So let's look at an example. So I'm going to draw it as I read it out. So first let's put in an xy axis. So we have a car traveling on a bearing of 40 degrees, which just means we're going at a 40 degree angle from north in a clockwise direction at 120 kilometers an hour, which means we can express it with a vector that is 120 units in length. So this vector here is, you can imagine it as its length being 120 to represent the 120 kilometers per hour. Then we have wind coming from the west at 40 kilometers an hour. So coming from the west would be in this direction. And we can imagine that vector having a length of 40. And we want to know the overall movement of the car. So the car is traveling in this direction at a bearing of 40 degrees. Wind coming in from the west at 40 kilometers per hour. Yeah, the car's traveling at 120 kilometers per hour. What's the overall movement of the car? Well, the overall movement of the car is going to be the addition of these vectors. So you can use the parallelogram law of addition, or you can just imagine the wind vector moved up here, joining the tail to the head of this one, and the overall vector is going to be this vector here. So, but we need some expressions for some of these vectors. So let's call the car vector C, and we'll call the wind vector W, which means that this vector is going to be C plus W. But we need some better expressions for C and W. So C, we can use the fact that we have the angle and the length of the vector. So if this angle here is 40 degrees, this angle inside, because we just like measuring from the positive x-axis, is going to be 50 degrees. And we know its length is 120. So we can express the vector c as 120 times cos 50 I plus 120 sine 50 j. And w we can just express as 40 I, because it has a length of 40 in the positive x direction and it has no y component. Then if we want the vector c plus w, all we need to do is add up the x components together and the y components together. So we're going to get 120 cos 50 plus 40 I. And there's no y component for w, so it'll just be 120 sine 50 j for the y component. Now, all we have to do to get the overall movement of the car is to just find the magnitude of c plus w and the angle that it acts at. So the magnitude of c and w is just going to be the square root of 120 cos 50 plus 40 squared plus 120 sine 50 squared, all square rooted. And if you do all that, you're going to get 168.2 kilometers per hour. Finding the angle that it acts at, that's just going to be tan theta equals its y component over its x component. So it's going to be 120. So this is of c plus w. So the y component of c plus w is 120. 120 sine 50 over 120 cos 50 plus 40. And that's going to be about 1.03. And we just inverse tan that to get theta. And throwing that in the calculator is going to give us 45.9 degrees. So overall, the car moves at an angle from here to here at 45.9 degrees at 168.2 kilometers an hour, which will end up being the length of that vector there.